Today we're going to talk about solving log and exponential equations. There's a few basics that you should basic laws of exponents and logs that you should have at your fingertips to help you through some of the problems here. So I'll call these basics. First of all, a couple that we talked about in class today is that the log base a of a to the x is equal to x. That means the exponent on a that will give you a to the x is equal to x. And then the same law as far as the natural log goes is the natural log, this is log base e of e to the x is equal to x. And then there are a couple of exponential basics that you should know. First of all, if you have a base a and you raise it to the log base a of x, it's equal to x. And I'll show you in a minute how this will work. And if your base is e instead of a, this is e to the natural log of x, and that is equal to x. So I'll show you how that works. For example, if I have the base a be 2, if I raise 2 to the power of the log base 2 of 16, it should be equal to 16, this value. We know that the log base 2 of 16 is equal to 4, and 2 to the 4th is 16, so that number matches. So that kind of proves our little basics here, our premise. And I'll just give you one more example. If we have the base of 3, if we take 3 to the log base 3 of 9, well, the answer should be 9. Well, let's see if it is. The log base 3 of 9 is equal to 2, and 3 squared is 9. So that's how that one works. So we're going to use some of these basics to solve an exponential equation. But what we do is we use logs to solve exponential equations. An exponential equation looks like this. The most basic of all basic kinds is something like e to the x is equal to something. Let's say e to the x is equal to 15. If you want to solve that for x is in the exponent, and you can't write these as the same basis. So if you want to solve for an exponent, what you have to do is take the log of both sides. Well, since this is base e, we're going to take the natural log of both sides. The natural log of e to the x is equal to, if you take the log of the left, you've got to take the log of the right, natural log of 15, log both sides. And from up above, the natural log of e to the x is x. So x is equal to the natural log of 15. You can put parentheses around if you want, but you don't have to. And if you don't have a calculator of any kind, you can just leave that as the natural log of 15. Or if you want to take it to 3 decimal places, you can just turn your calculator on and type in the natural log of 15, which is 2.708. So that's approximately 2.708. So that's the first little example. Second little example, number 2, we'll just get a little bit more algebra involved. If we have something like 4e to the 2x plus 1 minus 8 equals 200. We just have to go through a couple of algebra steps. Our job is to isolate the base with its exponent. So we see the exponent is where the variable is, so that means we have to use logarithms. But first we have to isolate the e to the 2x plus 1. So you're going to add 8 and divide by 4. So you'll have e to the 2x plus 1. Well, 200 minus 8 is 192. And 192, I'm sorry, you're going to add 8. Sorry. Add 8 to both sides. You get 208. And then 208 divided by 4 is 52. So e to the 2x plus 1 is equal to 52. Add 8 divided by 4. And then to get rid of the e, so you can just be left with 2x plus 1, you're going to take the natural log of each side. So the natural log of e to the 2x plus 1 is equal to the natural log of 52. And it's almost like saying the ln and the e cancel each other out, even though it's not a true cancel. But you're left with 2x plus 1. You're left with the exponent is equal to the ln of 52. And if you want to solve for x, subtract 1 and divide by 2. So x is equal to the natural log of 52, subtract 1, divide the whole thing by 2. And if you're not allowed a calculator, that's how you would leave your final answer. But if you do have a calculator and you want to round it to the nearest thousandth, just grab your calculator and you'll do the natural log of 52, close parentheses, minus 1, all over 2. And it looks like it's about 1.476, if you wanted to round that up to the nearest thousandth, 1.476. All right, here's a third example. We'll do an example that is not base e. We'll do an example that's base 3. So let's say you have 10 times 3 to the half x minus 3 plus 7 is equal to 70. You want to isolate the base with its exponent. So you're going to subtract 7 this time. Hopefully I'll do it right. Subtract 7 and you get 63. And divide by 10 so you get 6.3. And you'll get 3 to the 1/2 x minus 3 is equal to 6.3. Subtract 7, divide by 10. And now instead of taking the natural log of both sides, because it's not base e anymore, it's a base 3, you're going to take the log base 3. So we'll take log base 3, because that's the base, of 3 to the half x minus 3 is equal to the log base 3 of 6.3. And this log base 3 and this 3 go away, and you're left with a half x minus 3 is equal to log base 3 of 6.3. And if you want to solve that for x, add 3 and multiply by 2. So you're going to add 3 to both sides to get rid of that 3, and you're going to multiply the whole thing by 2 to get rid of the 1/2. So x is equal to log base 3 of 6.3 plus 3 times 2. And hopefully you're doing this along with me with your calculator so you can get practice putting this in. For the people who don't have an 84 and you can't do the log base anything, you can use a change of base formula, which is saying that you could do the log base 3 of 6.3 as log of 6.3 divided by the log of 3 plus 3 times 2 to evaluate that. We get the log of 6.3 divided by the log of 3, oops, forgot my parentheses, plus 3, multiply that by 2, and your answer should be about 9.351, if you rounded that correctly. 9.351. The next thing we're going to do is solve log equations. And most of the time when you solve log equations, you have to use it's best to write it as an exponential equation. This is just a review from Algebra 2. I know you solved log equations last year, but here's the refresher. Solving log equations, often it's best to rewrite as an exponential equation. So for example, suppose we have to solve 3 times the natural log of x minus 1 plus 1 equals 6. Going through a couple of algebra steps, I hope this is clear. Going through a couple of algebra steps, you subtract 1, You get 5 divided by 3, so you get the natural log of x minus 1 is equal to 5/3. And in order to solve this for x, since this is log base e, you're going to take e to the 5/3 and make that equal to x minus 1. That's rewriting a log equation as an exponential equation. And then you're just going to add 1, and so you'll get e to the 5/3 plus 1 is equal to x. No calculator, you leave it like that. But if you do have your calculator, you can approximate that as second ln of e to the 5/3 plus 1. Looks like the answer is 6.294, approximately. Sometimes when you're solving a log equation, you have to condense the logs first. If you have more than one log expression or more than one term that has a log in it. Oops. Sometimes you need to condense logs, and that's by using log rules, product rule, power rule, quotient rule. Remember, there's 3 log rules that you have to keep in mind. So for example, maybe you'll have a log equation that looks like this: the natural log of x minus 2 plus the natural log of 2x minus 3 is equal to 2 times the natural log of x. Well, when you have 2 logs, 2 terms with a log in it, and they're separated by a plus, they're added together, this is the product rule, and the product rule says you're going to take those 2 logs and condense them into one log, and you're going to multiply those arguments. So x minus 2 gets multiplied by 2x minus 3. And over on this side, you can condense this log by putting the 2 as an exponent on x, so you can call this the ln of x squared. That's the power rule in reverse. And now you have to keep in mind, when you have one log term on the left, one log term on the right, when the log of A is equal to the log of B, whatever A and B might be, if they're equal to each other, then you can assume that A is equal to B. It's almost like canceling out the word log. You don't cancel functions, but it's kind of that idea. So in this example, because the log of this is equal to the log of this, you can just say that this argument is equal to this argument. If I want to solve this, I'm going to have to FOIL it first. So if I multiply x minus 2 times 2x minus 3, I'll come up with 2x squared minus 7x plus 6, and that's equal to x squared when you get rid of those logs. Setting it equal to 0 by subtracting x squared from each side, you get x squared minus 7x plus 6 is equal to 0, which is factorable, minus 6 minus 1. So you get x is equal to 6 and x is equal to 1. With log equations, you have to make sure you don't have an extraneous solution in the end. So you're going to go and take these solutions and plug them in to the original equation for your little check. So your check says, does the natural log of 6 minus 2, which is 4, plus the natural log of 12 minus 3, which is 9, equal 2 times the natural log of 6. You're going to check x equals 6. So we can put that into our calculator. Does the natural log of 4 plus the natural log of 9, whatever that may be, does that equal 2 times the natural log of 6? That's our little check. And those two numbers are the same, so this one checks. X equals 6 is good. And now we're going to check x equals 1. If we plug 1 into the original equation, we'll get natural log of negative 1 plus the natural log of negative 1. Is that equal to 2 times the natural log of 1? Well, we can stop right there because the domain of a log is got to be all positive numbers. Negative 1 is not a positive number. You can't do that. You can't take a log of a negative number, because the domain of a log function is x is greater than 0. So right now we can say x equals 1 is an extraneous solution, so that's rejected. The only answer to this problem is x equals 1. We'll do another log example. Let's say we have a log base 2 of x plus 5 minus log base 2 of x minus 2 equals 3. Well, this one's different than the other one because this has a log on the left side of the equation but no log on the right-hand side. Well, we're still going to have to condense because we have two logs separated by subtraction, so condensing that, you make one log base 2, and this is the quotient rule, so x plus 5 is divided by x minus 2, and there's nothing to do on the right-hand side. So since we have the log of something equaling a number, we can rewrite this exponentially. In other words, as an exponential equation. So this is going to say 2 to the third is equal to x plus 5 over x minus 2. And to solve this for x, you're just going to multiply both sides by x minus 2 to get rid of that denominator. And 2 to the third is 8. So 8 times x minus 2 is equal to x plus 5. Distribute and then solve for x. So 8x minus 16 equals x plus 5. Subtract x and add 16, so you've got 7x is equal to 21, so x is equal to 3. And then if you want to check that, you can plug in x equals 3 to the original problem. So the check is, does the log base 2 of 3.5, 3 plus 5, which is 8, minus the log base 2 of 3 minus 2, which is 1, is that equal to 3? Well, the log base 2 of 8 is equal to 3, because 2 to the third is 8. The log base 2 of 1, the log of 1, no matter what the base, is 0. So without even a calculator, you can check and show that x equals 3 is the solution to that problem. The next thing I want to show you is that there's a formula for calculating compound interest. I think you were introduced to it last year, but we're going to go over a couple of examples with this formula. What I'm going to do here is I'm going to stop the video and I'm going to create a second video because I had trouble uploading, I think because the video is a little bit too long. So I'm going to stop here. I'm going to continue and you're going to watch the second video, which is just a couple of examples using this formula. So stay tuned.